Hello friends, this is Priyanka. Today we are going to solve a problem on three-stage compression refrigeration system with flash chambers. So first I will read what is the given problem. An ice plant working on ammonia as a refrigerant works between overall pressure limits of 2.5 bar and 15 bar. It is fitted with expansion valve with vapor extraction at 5 bar and 10 bar. The load on the plant is 10 tons of refrigeration. Find the circulation of refrigerant through the condenser and the power required to drive the three compressors. Use pressure enthalpy chart. So this was the given problem. So let us first understand what is the given data and which factors we have to find out. Now if we observe this problem, here are three-stage compression refrigeration system is used and the flash chamber pressure is also given. That means there are two flash chambers within this three-stage compression system. So here the pressure limits is given. So we know that the minimum pressure is for the evaporator and the maximum pressure is at the condenser. So we can say that P, that is 2.5 bar, and PC, that is the condensation pressure, that is 15 bar. Now the flash chamber pressure is also given. So this flash chamber, F2 is there 5 bar and F1 is there for the 10 bar, and the load on the evaporator is Q, that is 10 TR, that is also given. And we have to find out what is the mass of refrigerant that is passing through this condenser, as well as we have to also find out what is the power required to drive the system. We have to first find out the enthalpies at the different points during the processes taking place in this three-stage compression system. So we will consider the point 1 where the refrigerant is entering into this low pressure compressor. So what is the state of this refrigerant? So it is at saturated vapor state, because before entering into this low pressure compressor, it is leaving from this evaporator. So pressure is equal to evaporator pressure P, and the state of the refrigerant is at the saturated vapor state. So here is the pressure enthalpy diagram that is provided in the examination for the ammonia refrigerant. So if we observe, this is the saturated liquid line and this is the saturated vapor line. So we will select first where will be the point 1. Now if we observe at the pressure, evaporator pressure, that is 2.5 bar, that is this PE is equal to 2.5 bar pressure line, and here is the saturated vapor line. So point of intersection will give us the point 1, and here H1 is equal to 1425 kilojoule per kilogram. Now what happens in this low pressure compressor? Compression process is taking place at constant entropy. So we have to select what is the entropy at this point 1. So entropy at this point 1, that is S1 is equal to 5.55, and that is S is equal to 5.55, and along this line the compression process is taking place. Now what is happening in this three-stage compression system? After compression means compression is taking place up to the condenser pressure. So if we observe this line meets, that is entering, the refrigerant is entering directly into the condenser. So here we have to compress this up to the condenser pressure, and condenser pressure is 15 bar. So here we have to select the 15 bar pressure line, and along the line of this 5.55, that is entropy, we have to select the point of intersection, that is at 15 bar. So here is the point 2, and what is the H2? That is 1660. Now again we will move for the next. So again there is the intermediate pressure compressor. Now if we observe what is the process of compression, that is 3 to 4. So now this point 3, what is the pressure for the refrigerant at the point 3, where the refrigerant is entering into this intermediate pressure compressor. So if we observe, it is incoming from this flash chamber F1. So what is the F1? That is equal to 10 bar. So here it is given that flash chamber pressures is given 5 bar and 10 bar. So here we have to write here will be PF1, that will be 5 bar, and PF2, that will be 10 bar. So for this F1, that is PF1 5 bar, we have to write here, and for this pressure of 5 bar we have to select the point 3. So what is the state of the refrigerant? Now if we observe, this flash chamber separates the liquid refrigerant and vapor refrigerant, and vapor refrigerants are passing for the compression through this point 3. So we can say that this point 3 is on the saturated vapor line, and at the pressure F1, that is 5 bar. So we have to select here F1 5 bar pressure line, and this is the saturated vapor line. So point of intersection will give us the point 3. So what is the enthalpy at this point 3? So if we extend this point, here will be H3, and H3 is equal to 1432 kilojoule per kilogram. So this is the enthalpy at the point 3. Now what is happening after compression? So compression process is 3 to 4. Now here is the point 4. So refrigerant is passing towards the condenser, that is the compression process is taking place up to the condenser pressure. So again, what is the entropy at this point 3? Because this compression process is taking place at the constant entropy. So H3 is equal to 5.32. So along this line we have to take this PC, condenser pressure 15 bar, and we have to select the point of intersection will give us the point 4. So what is the enthalpy at this point 4? H4 is equal to 1600. So if we extend this point 4, will give us here the value of H4. Now again, if we move next, so what is the next process? That is high pressure compression. Now there is the point 5. So for this point 5, if we observe this point 5, the refrigerant is at pressure F2, that is the pressure at flash chamber 2. And what is the state of this refrigerant? Now here only vapors are passing through this point 5 for the high pressure compression. So we have to select the saturated vapor line and pressure equal to F2, that is 10 bar. So PF2 is equal to 10 bar, and here we will select the point 5. So what is the enthalpy at this point 5? That is 1445 kilojoule per kilogram. Now again, this compression is taking place at the constant entropy. So what is the entropy at this point 5? So at this point 5, entropy is 5.05. Now this process of compression is taking place up to a condenser pressure. So again we have to select the point of intersection for this 15 bar pressure line, and this is the entropy. So here is the point 6. So again if we take here H6, that will give us 1510 kilojoule per kilogram, that is the enthalpy at point 6. So in this way, now we will move the next. So after this high pressure compression, if we observe the refrigerant leaving after compression from this low pressure compressor, intermediate pressure compressor and high pressure compressor are meeting or mixing with each other. So again, and all are moving to this condenser for the condensation process. So what is happening in the condenser? So these refrigerants at high pressures are getting cooled and getting converted up to the saturated liquid state. So we have to show this condensation process, that is from 6 to 7, that is the refrigerant is getting converted into the saturated liquid state. And what is the pressure? Pressure is the condenser pressure, that is 15 bar. So along this same pressure, the cooling process is done up to this saturated liquid line. So this is the pressure line and this is the saturated liquid line, and this point of intersection will give us the point 7. So again this point 7 means what is the enthalpy at this point 7. So this point 7 is on saturated liquid line, so we will say that HF7, and HF7 is equal to 352 kilojoule per kilogram. Now if we again move next from 7 to 8, here is the expansion one. So expansion process is taking place at constant enthalpy. So expansion means what? Expansion means decrease in pressure. Now this condenser pressure is getting decreased up to the pressure of flash chamber 2. So what is the pressure? That is 10 bar. So from this 15 bar to 10 bar, the pressure is getting decreased at constant enthalpy. So we have to show that. Now if we observe this point 8, what is happening? This point is in between saturated liquid line and saturated vapor line. That means there is the mixture of liquid and vapor. So when it is moving towards this flash chamber, what is happening? Flash chamber separates it into the liquid refrigerant and vapor refrigerant. And this vapor refrigerant are passing for this high pressure compression for the process of 5 to 6. So here is the process of 5 to 6. So we have to show from this point 8, we have to show arrow towards the right hand side up to this saturated vapor line, and here is the vapors. So this is the arrow, and where is the liquid refrigerant? So liquid refrigerant is leaving from this point 9 for the next process. So we have to select this point 9 on the saturated liquid line, and here is the process 8 to 9. So liquid refrigerant will be at point 9. Now if we observe here, we will consider what is the mass of refrigerant. That will be for this expansion from 7 to 8, we will consider this mass will be m. And then after separation, so this total mass at this point 8 will be m, that is liquid plus vapor. But what is happening after separation? Mass of refrigerant, that is in the saturated vapor state, we will say here m5, and the mass of refrigerant, that is in the saturated liquid phase, that we will say that m9. So this total mass is m. So we can say that m is equal to, is getting separated into these two, saturated vapor and saturated liquid. So m is equal to m5 and this m9, that is getting separated. Now again if we observe this point at the point 8, what is the enthalpy? That is also equal to HF7, and that is 352. Now we have to select what is the dryness fraction at this point 8. So this dryness fraction at this point 8, that is x8, and that is equal to 0.06. So that will be available on the pressure enthalpy chart that will be provided in the exam. So its notation is x. So we have to find out what is the value of x at the point 8. Now why it is important? It is important to calculate this mass at this point 5 and this point 9. Then again if we move the next point, that is here will be the point 9. So again it is important that what is happening from this 9 to 10. So 9 to 10 again expansion wall is there, that is the expansion process is taking place at the constant enthalpy. So this expansion process is taking place up to a pressure of F1. So F1 pressure is 5 bar. So we have to show that from 10 bar to 5 bar at constant enthalpy. Here is the pressure. Now at this point 10, again if we observe the refrigerant at this point 10, refrigerant is in the liquid plus vapor form. So again this flash chamber F1 separates the vapor refrigerant and liquid refrigerant. Now if we observe this vapor refrigerant are passed for this compression process at point 3. So again we will take here the vapor refrigerant passing towards the point 3 and liquid refrigerant for the next expansion process, that is at point 11. So here is the point 11. So make here the point that is 11. Now again if we observe, there is the expansion process for the 11 to 12. So again expansion process is taking place up to a pressure of evaporator pressure, because next it is moving towards the evaporator. So if we observe, we will consider the mass of refrigerant at point 11, that is the liquid refrigerant M11 and vapor refrigerant, that is M3. Now again we have to show the expansion process at constant enthalpy, and what is HF11 is equal to H12, which is equal to 198 kilojoule per kilogram. So again we have to find out what is the dryness fraction at this point 10. So we can say that X10 will be there. So if we observe the enthalpies at all the points are getting here selected. Now again there is the evaporation process, that is 12 to 1. So we have to show that at the constant pressure, that is PE. So this process of evaporation will give us the refrigeration effect, and refrigeration, for the calculation of refrigeration effect, load on the evaporator is also given. So it is easy to calculate the given data. Now if we observe, we have to calculate the mass M. So what is this mass M? So in the given problem, it is clearly noted that we have to find out what is the mass of refrigerant that is passing from this condenser. So this mass M passing from this condenser, that means the mass of refrigerant in the condenser is at the saturated liquid state. So here at point 7 we have to find out what is the mass. So we will consider here the mass M, and again it is getting splitted into this M5, M9, or here that M3, M11. So that will be the next process. And again the next question was, we have to calculate what is the power required to drive the system. So for that we have to find out what is the work done that is taking place for this system. So work done is taking place at these three compressors, that is low pressure compressor, intermediate pressure and high pressure compressor. So for that it is important to calculate what is the mass of the refrigerant that is moving for this compression process. Now we will calculate what is the mass M of the refrigerant passing through this condenser. So here is the formula: 210 Q divided by 1 minus X10 multiplied by 1 minus X8 multiplied by the enthalpy difference during this evaporation process, that is H1 minus HF11, or we can say H12. So here we can take what are the values. So 210 Q, that is given 10, then 1 minus X10, so X10 0.08 and X8 0.06. So H1 value 1425, and what is the value of HF11? That is 198. So when we put all the values, we will get the mass M, that is 1.98 kilogram per minute. So it is easy for the calculation that when we know all the values from this pH diagram. Now we will move for the next. So what is the next question? That means we have to calculate what is the power required to drive the system. So power is equal to work done by 60. So work done means work done at this low pressure compressor, intermediate compressor, plus this work done at high pressure compressor. So we will calculate what is the work done at this low pressure compression. So low pressure compression, that is the process 1 to 2. So we will observe here, this is the process 1 to 2. So what is the work done? So we know that during the process 1 to 2, what is the mass of the refrigerant moving for this low pressure compressor multiplied by the enthalpy difference during the compression. So what is the enthalpy difference? That is H2 minus H1. And what is the mass of the refrigerant that is moving in this low pressure compressor? That is mass M1, and that is equal to mass at this point 11, that is M11. So now how to calculate this M11? But if we observe, we know what is the mass in the condenser. So in terms of M, we have to write here the formula for this M11. So how to write? So M multiplied by 1 minus X10, that is, this is at this point 1 to 2, there is the compression process is taking place, but we have the value of M, that is here is M, but we want the value of M11 because this same mass is provided to this low pressure compressor. So what is the formula? We have to consider the dryness fraction at these two points, that is 8 and 10, because the compression process is taking place here. So here m multiplied by, that means this m multiplied by 1 minus x10 multiplied by 1 minus x8 multiplied by this enthalpy difference. So when we put all the values, we will get the WL is equal to 402.4 kilojoule per minute. Now we will move for the next. Now what is the work done at this intermediate pressure? So if we observe, mass M3 is passing for this compression towards the intermediate pressure compressor. So here is the mass M3, that is at point 3, and here is the compression 3 to 4. So we have to take M3 multiplied by the change in enthalpy, that is H4 minus H3. So here is H4 minus H3. But how to calculate this mass at point 3? So we have this mass M. Here is the mass M. So how to write here? So before that, if we observe, here is the dryness fraction, that is x10 and x8. Now this mass M3 is at the dryness fraction. So before it is getting separated, the dryness fraction is x10. So we have to multiply with m multiplied by x10 multiplied by 1 minus x8 multiplied by enthalpy difference. So if we put here the values, it is equal to 25 kilojoule per minute. So when we solve this work done with the help of diagram, it is easy to remember these formulas or to make these formulas. Then we will move for the next. Now for this high pressure compression, mass M5 is there. So how to calculate this M5? So M5 multiplied by the enthalpy difference during the compression, that is H6 minus H5. So M5, so we will write here in terms of M. So here is the mass M5, and if we observe, the before it is getting separated, the dryness fraction is x8, and so we have to take the previous mass multiplied by this x8 and multiplied by this x6 minus h5. So when we put all the values, we will get the work done, that is 7.72 kilojoule per minute. So we will add now these three work done, that will be the total work done. So when we add this total work done, WL plus WI plus WH divided by 60, which is equal to power. So 435.12 by 60, which is equal to 7.25 kilowatt. So this is the answer.